probability distribution for a continuous random variable, and the first thing is the normal distribution. So quickly we will recall what is this continuous random variable. So first of all, the random variable is nothing but it is a function. It is a function. Just it is a function from the sample space to the set of real numbers. Okay. So in statistical terms, this is the random variable x. When we define a random variable x from the sample space to the real numbers, if the range set is interval or union of intervals, okay, then we will say that this x is nothing but a continuous random variable. And if its range set is finite or countably infinite, then we will say that it is nothing but a discrete random variable. For the discrete random variable, we saw 4 different probability distributions. For a continuous random variable, the first distribution that we are looking at, the normal distribution. Even the word, even if the word says that it is normal, but let me tell you, it's not that normal. Even the probability density function for continuous random variable, we saw that the probability is nothing but, what is it? For continuous random variable, probability is assigned to an interval. Okay, and whenever I want to find out the probability for an interval, what I have to do is I need to integrate the probability density function and under the given interval, and then we will get the probability. So whenever I will define different distributions in for continuous random variable, we will first of all define the probability density function. So a continuous random variable x, a continuous random variable x is said to follow normal distribution, is said to follow normal distribution with parameters with parameter mu and sigma square if its probability density function is f of x equal to 1 upon sigma under root 2 pi e to the power minus 1 upon 2 sigma square in bracket x minus mu whole square. Let me just write it down a bit. E to the power minus 1 upon 2 sigma square x minus mu whole square. Okay, so this is the probability density function. Now, if you want to find out the probability for this in the interval, say 1 by 2 to 3 by 2, what I will have to do? If I want to find the probability from 1 by 2 to 3 by 2, quickly, for a continuous random variable, this is a probability density function. How do you get the probability now?
Integrate.
Integrate this function from 1 by 2 to 3 by 2. So you can see that this thing becomes really difficult. I mean, if integrating this for such small values, uh, it is going to make the things difficult. Okay, but there is a shorter way to this. There are certain what you say important properties about this normal distributions, and it will make a lot of things easier here. And how it is going to make the things easier is by, say, for an example, I have the okay, let me just write it down as remarks. First and very important one, uh, what is the notation? X follows normal distribution with parameters mu and sigma square. So we saw yesterday, what do we mean by a parameter? A parameter is something that will define the distribution completely. In this case, uh, the parameters for the normal distribution are mu and sigma square. What was the mu? I mean, used for earlier. Earlier, mu was used for in probability. Where do you use mu? Mu is used to denote. कहाँ पे यूज किया है म्यू? Okay, at least tell me sigma square. Where have you used sigma square? Where have you used sigma square? You don't know where you used mu. What was denoted by mu? What you denoted by
Variance.
sigma square is for variance. Mu,
Variance.
Moment.
Mean.
mu is mean. Exactly. So thus mu is the mean for the distribution, and sigma square we denoted, we use the sigma square to denote the variance, and the same thing is there. Later when we use the formula to find out the mean for this distribution, we'll come to know that mu is nothing but the mean. Fine. There is a very important thing about normal distribution is that in normal distribution, mean becomes equal to median becomes equal to mode. All three of them are equal for normal distribution. This is a bell-shaped curve. Okay. Third one. Probability density function for normal distribution. Normal distribution is bell-shaped curve. What is important about the bell-shaped curve? While studying statistics, I told you that I introduced you to the two concepts. One was kurtosis, other was skewness. Does anyone remember what it was? What it was?
Sir, kurtosis was the peakness of the curve.
Peakedness of the curve, and skewness was to which direction your curve is stretched. Okay.
Yes.
So these two things we saw in the statistics. So if it is there is a large peak, there is no peak, so you say that it is platycurtic. If there is a large peak, then it is leptocurtic, and there is no curve, so it is mesocurtic. And skewness is that it is stretched in some direction. It may be stretched in the left hand side direction, it may be stretched in right hand side direction, and so on. Okay, so in normal distribution, there is no peak is there, neither it is platycurtic, nor it is leptocurtic. Also, it is not stretched in any of the direction, so that's why it is a bell shaped curve. If I have to draw a diagram for the bell shaped curve, so it will be like this. Looks a proper bell shaped curve. It is neither stretched in left hand side nor in the right hand side. Whatever is on the this is the mu actually. Can I say that this is mu? Looking at the second remark, can you say that this is mu? Can you say that?
Yes, sir, because it is equal for kurtosis.
Okay, anyways, we'll come to this later. So this is nothing but the bell-shaped curve. Next remark. So when we are talking about this normal distribution, in this case, it is a bell-shaped curve. So data may differ. I mean to say that in some cases, the bell-shaped curve that we have may be here. Okay. In some cases, it may be shift on the right-hand side. I mean, according to the data, this is shift somewhere. In some cases, the bell, the structure that we have, it may be larger. By larger, I mean to say it may be uh, this kind of structure. But still, it is a bell. But still, this is a bell-shaped curve. So depending on the data, what things may vary? There are two things those are varying. Either the bell will be shift either in the left hand side or in the right hand side, or the size of the bell is large, or the size of the bell is smaller. Are you getting my point? But it is a bell. So bell is shifted, or it is large, it is small. So two, but can I say that all of them are similar? Yes or no? I'll just recall one concept from your school mathematics. Similarity of triangles. What do you mean by similarity of triangles? And you said that by SES test, SSS test, the corresponding angle of uh, corresponding triangle. something like that. I don't remember the exact words. What do you mean by symmetry, similar there? Anyone? Quickly,
Means
So
the
if they
side.
are congruent.
they are congruent. Congruent is a different thing. I mean, similarity is different. Congruent, you say that
Then
even
corresponding angles are similar to each other.
yes, similar. I want to understand what was that similar. Congruent, you say that
They
Proportion.
are proportion also.
they are proportionate
So
to
the
each other.
angle between both is same.
I mean the relation is same. So if
Yeah.
the larger, if two or three sides of the triangle of two triangles are just the multiples of each other by 2 units, then angle has to be there in the same multiple. Okay, so by the ratio they are same. By congruence we mean that those are exactly the same. So in similar sense, these all are bell shaped curves, those all are similar to each other. Okay, so no matter how many normal distributions you study, those all are going to be similar to each other. And how they are going to be similar? The similarity will depend on mu and sigma. So to make our study uniform, this third remark plays a major role. So if mu is equal to 0, sigma square is equal to 1, then the normal distribution then the normal variable, sorry, normal variable is called standard normal variable. And is denoted by z and is denoted by z. Then the probability density function is, then the probability density function is, yes, what it will be? By looking at the above function, your f of z will become
1 by root 2 pi e power minus 1 by 2
1 upon under root 2 pi
e power
minus
1 minus 1 by 2
minus 1 by 2 into
x square.
z square. The new variable you are defining z, right? So what I have done here is, I mean, what we are doing here is, as I said in the previous remark, that it is a bell-shaped curve. It may be shifted to somewhere. I mean, it may be larger, it is smaller. Okay. So by this transformation, so what is the transformation? If you see, if it is, I can also say that roughly it is, I'm substituting z is equal to x minus mu by sigma. When you take z is equal to x minus mu by sigma, what happens is, we have seen this in statistics earlier. What is it? Change of origin and scale? Yes or no?
Yes,
By
sir.
how?
Yes, sir.
By how many, Ajay? By how many units you have shifted the origin? By? Have you shifted the origin? Anyone else? By how many units you are shifting the origin?
Sir, by mu.
By mu. Okay. What is mu? Mu is nothing but the mean. And by what scale you are changing the variable by? The standard deviation. So just understand what you are doing here. No matter where your curve is, I just said that we have a bell-shaped curve. It may be somewhere here like this. Okay, let me draw just one large diagram. Okay, say if this is 0 here. So even if it doesn't look, consider it as a bell-shaped curve. Okay. So all the three are bell-shaped curve here. Okay. This is the mu for the first one. Okay. So I'll call this mu1. Mu1 is simply 0. This is mu2, which is not equal to 0. This is mu3 for the third curve. Call this first curve C1, second curve C2, third curve is C3. In the similar manner, these curves are going to be anywhere. I mean, whenever you say a normal distribution, it will have some mean, it will have some standard deviation, sigma 1, sigma 2, sigma 3. So when I subtract, what will happen? So if this change, I am doing this in this curve C3, what will happen? Z is equal to, what is your x? Mu3. Mu3 minus mu divided by sigma. What do you mean by mu? Mu is nothing but the mean for that
Mean.
distribution, right? So this will become 0. So what you have done after making the change of variable, z will become 0, yes or no? Manas, is the value of z will become 0 at mu3 now?
Yes, sir.
Yes. Aditya?
Yes, sir.
Yes. So what you are doing is, you are, wherever your curve is, you have shifted it to origin. So what I'm trying to do, I'm trying to bring uniformity in my calculations. Okay. So this is a very important step. Whenever any of the distribution is given, we will first of all change my variable. Put z is equal to x minus mu by sigma, standard normal variable, what we call it. Okay. And if there is a large curve, I can make it smaller by dividing by this. By sigma, I am changing this. Fine. I hope I have made myself clear what is the need to convert the original variable x to standard normal variable. Okay. So in this case, the fourth remark, Mu is called the location parameter. Mu is location parameter. Location parameter. And sigma is called scaling parameter. Is called the scaling parameter. The next thing what I will check is now whether it is a probability density function. What were the conditions so that this will become a probability density function? What were the conditions? If I give you a function f of x and I tell you to check whether the given function is a probability density function or not, what will you do?
F of x should be greater than or equal to 0.
The first thing, and second,
Integration of f of x from minus infinity to infinity should be 1.
exactly. So the first case f of x, whether it is greater than 0, always we can look at the function f of x. So e raised to any number, whatever it is, positive, negative, it is always going to be greater than 0. Standard deviation, is it positive always? Standard deviation, is it positive always?
Yes, sir, it is 0 or positive.
Why? The definition of standard deviation is defined like this. It is the positive square root of the variance. Standard deviation is nothing but the positive square root of variance. That's why it is always positive. Okay, and that's why f of x is I have scaling parameter. I've written this spelling wrong. Yes. So f of x is greater than or equal to 0 always. And integration minus infinity to plus infinity f of x dx. This is equal to 1. Consider that I am right and integration is always going to be 1. Because it will require some higher gamma function kind of integration. So right now just consider that yes, whatever I have said it is correct. Fine. So what is the use of this now and how we are going to find out the integration? That is the part which is actually needed to understand this. So now sixth remark. It is a bell-shaped curve. I'll talk in terms of standard normal variable. In terms of standard normal variable. What is standard normal variable? What is a standard normal variable?